sometimes when we are working with trigonometry, rather than using our calculators, which give us decimal answers which are rounded because they go on for too long, sometimes we want to have exact values. In other words, we want to leave things with the square roots, which are sometimes necessary, or just the fractions that we come up with as fractions, so that we don't have it rounded. So in order to do that, there's some special angles. When we talk about special angles, we're just talking about some common benchmark type angles. And in particular, we're talking about 30 degrees, 45 degrees, and 60 degrees. Those ones make sense, right? Between 0 and 90 degrees, those ones would be standout ones. 30 degrees is 1/3 of 90. 45 is half. 60 is 2/3 of 90. So it's good to have those special angles, the exact values of them, at our fingertips. So I'm just going to take a moment to show you where they come from. So for the 45 degree triangle, to find out the exact value of a 45 degree angle, let's start with a square with side lengths of 1 unit. So that means that the length of this side is 1, whatever the units are. You can think of it like centimeters, meters. I won't put units on there though. Being a square, that means that this side is also 1 unit. This side, which would be the hypotenuse of the triangle, if I was just to focus on this part of the triangle, make it into a right triangle now, this would be my hypotenuse, wouldn't it? And the hypotenuse is from Pythagorean theorem, we know it's going to equal the sum of the other two sides squared, then added together, and then we take the square root of it. So if I take the square root of one side, add the square root of the other side, the other two short sides, and then take the square root of that, that's Pythagorean theorem. Well, 1 squared is 1, plus 1, another 1 is 2. So the hypotenuse, the length of that side, if the other two sides are 1 each, is going to be 2. So I know the hypotenuse for this triangle is 1. Let's say that the angle, it doesn't matter which corner I put it in, but let's say the angle is down here. That would make this the opposite side. So the opposite side length is 1, and the adjacent side length is also 1. So based on that, I can make up some trig ratios for a 45 degree angle. Sine is opposite over hypotenuse, so that would be 1 over root 2. Cosine is adjacent over hypotenuse, so that would be 1 over root 2 as well. And tangent is opposite over adjacent, that would be 1 over 1, but that just reduces down to 1, doesn't it? So those are 3 exact ratios for special triangles. So if someone says, what's the exact ratio for sine 45, I can say that it's 1 over root 2. Now of course that's an actual number. I could type that in a calculator. I could do 1 divided by the square root of 2. But as you can see, it gives me a big long decimal. And that's not even cut off. It would keep going actually longer than that. So that's an approximation. If I want to give the exact value, then I would just say 1 over root 2. Same for the same for the cosine, and obviously 1 is an exact value anyway for the tangent. So I want to develop some ratios like that for the 30 and 60 degree angles as well, because they're also special ones. So let's start in this case with an equilateral triangle that's got side lengths of 2 units. So this side length could be 2 units. That means this one's 2 and this one's 2 as well. But I'm going to probably erase that in a minute, because what I'm going to do is drop a straight line down from the vertex make this into a right triangle and just focus on this part here. If I do that, that means that this bottom part here has to be 1, right? Because this line here is a bisector of the side length, and since the side length of the whole equilateral triangle is 2, that means that shorter part has to be 1. And I'm not interested in what's going on over here anymore, but here I can find out what this side length is, again using the Pythagorean theorem. I know that the hypotenuse squared, so 2 squared, minus the other side, one of the other sides squared, which this one is, so minus 1 squared, minus 1 squared. If I take the square root of that, that's going to give me that side length. So that would be the square root of 4 minus 1, or the square root of 3. Now this is going to be the hypotenuse side no matter what, because in this triangle, that's obviously the one that's across in the right angle. I don't want to label this side or this side as opposite or adjacent yet, though, because it depends on which corner we're coming from. Down here in this corner, this would be a 60-degree angle, because remember we started with an equilateral triangle here, and equilateral triangles have 60 degrees in each of their corners. This corner up here is going to be 30, because it's half of the 60 degrees it was up in the top to begin with. If I add up these three angles, this one, and this 90, that adds up to the 180, so it all makes sense. But it depends on whether I call this side opposite or adjacent, depends on whether I'm coming from the 60 degrees down here or the 30 degrees up here. They're all going to, it's going to be different from each one. So let's focus on the 30 degrees for now. So for a 30-degree angle, that means I'm orienting myself from that angle up there in the top. So up here in the top, there's my 30 degrees. That makes this the opposite side down here because it's opposite the 30 degrees. And that means that this one here is the adjacent side because it's beside the 30 degrees, right? So I can do my trig ratios. Sine equals opposite over hypotenuse. Well, that's 1 over 2. Cosine equals adjacent over hypotenuse. That's the root 3 over the 2. And tangent equals opposite over adjacent, so that's 1 over root 3. Now, if I was to switch my focus, though, and instead of coming from the 30-degree angle, if I was to come from the 60-degree angle, then I'd have to relabel those two sides. I'd have to call this my adjacent side now, and this one would be my opposite because it's opposite from the angle that I'm focused on. So with that in mind, sine of 60 degrees would be root 3 over 2. Cosine would be 1 over 2. And tangent would be, adjacent would be root 3 over 1, opposite over adjacent. So root 3 over 1, which is just root 3. No, that's fine to leave them like this. Sometimes you're going to be asked to rationalize the denominator, though. That means to rewrite a fraction so that it doesn't have a radical sign in the denominator. Remember, the radical sign is that square root sign. So fractions that could be rationalized would be this one, where it's got the square root sign in the bottom, this one, and that's it. Those three could be rationalized because they all have square roots in the bottom to start with. So for example, if I had something like root 3 over 2, that's not one of the ones we have above, but if I had something like that, I can get rid of the square root in the bottom if I multiply the denominator by whatever the square root is. So if I multiply root 2 by another root 2, what I'll get, as we've seen before from working with radicals, is that would be the square root of 4 or just root 2. But I can't multiply only the bottom of a fraction by a number without changing the value of it. So if I do that, I need to multiply by the top by the same number as well. So I need to multiply both the top and the bottom by root 2. And as you can see, doing that here, starting with 3 over root 2, multiplying the top and the bottom by root 2. 3 times root 2 equals 3 root 2, and root 2 times root 2 equals the square root of 4, but that's just equal to 2, so this is the equivalent of this. They are equivalent, and we can prove that by looking at our calculator and just going 3 divided by square root of 2. You can see that equals 2.12, etc. or if I did 3 times the square root of 2 and then just divided by 2, I get the exact same answer. So those are the same values, just that this one here is considered to be more proper because denominators are supposed to be rationalized when we work with them. So, if you're asked to determine the exact value, you're being asked to work with these special angles. So there's a couple things you can do. You can memorize this chart, which I don't recommend, but I do recommend memorizing these triangles here. I can draw them very quickly from practice. I draw 2 triangles. I draw my 45-degree triangle, which I know goes 1, 1, and root 2 is the hypotenuse. And I draw my 60-30 triangle, which goes 1, 2, root 3. And then I can just create the trig ratios as I need to. So for example, sine 60 means that I'm going to do, there's my 60 degrees, I'm going to do opposite over hypotenuse. I know it's going to be root 3 over 2. So I can quickly come up with that fraction without having to have memorized the table. Tan 45, I'm going to go to the 45-degree triangle, and it's opposite over adjacent, 1 over 1. Tan 45 is just equal to 1. So minus 1 times cos 60. So back to the 60. Cos is adjacent over hypotenuse, or 1/2. Now I can just work it out using order of operations as usual. I've got root 3 over 2 minus 1/2. 1 times 1/2 is just 1/2. I should try to bring it together into a single fraction because, with a common denominator, they already have a common denominator, so that's handy. So I can just write this as root 3 minus 1 all over 2, and that would be my answer. In B part, we got sine. If you see a squared here, it means the same thing as if I had sine 45 and then I have the square out here. So that's what that is telling me. So it's telling me find what the sine of 45 is first, then square my answer. Tan 30, I'll just move on to, let's just write this out again and then start fresh on the next line. So I got tan 30 over sine 60. So sine 45 is this triangle. Sine is opposite over hypotenuse, so 1 over root 2. And then I'm going to square that, but I'll do that in the next step. Tan 30 means from here, I want to do opposite over adjacent, so 1 over root 3. Divided by sine 60. So this angle here now, which is opposite over hypotenuse, so root 3 over 2. One half squared means 1/2 times 1/2, which will be 1/4. And when I want to divide fractions, remember, even if it's just written like this, I can invert the one on the bottom. I'm dividing by root 3 over 2, so I can invert and multiply. So I can change this to 2 over root 3 and make it a multiplication. That means when I multiply, I'll get 1 times 2 as my numerator, and I'll get root 3 times root 3, which is root 9, or just 3 as my denominator. I need a common denominator to go any farther, so 12 would work. If I multiply 1/4 top and bottom by 3, I get 3/12, and 2/3 times 4, top and bottom is 8/12. Subtracting only the numerators, I have 3 minus 8 is -5. The denominator stays the same, and there's my exact value in that case. So that's working with exact values. I'm not using my calculator, I'm using the triangles, I'm creating the fractions, I'm working with them as they are. If it was necessary, I would rationalize the denominator. In neither of those two examples was that necessary, though. Use exact values to show that 1 minus sine squared theta sorry, 1 minus sine squared 30 is equal to cos squared 30. All right, so I can just do the left side and the right side separately. So the left side is 1 minus sine squared 30, which I already pointed out would be the same as sine 30 all squared. So sine 30, going back to my sketch again, there's 30. Sine is 1 over 2, opposite over hypotenuse. So 1 minus 1/2 squared. Following order of operations, 1/2 squared is 1/4. So 1 minus 1/4 equals 3/4. So I'm going to show by doing the right side separately, hopefully, that I get the same thing. So cos squared 30 is the same as cos 30 all squared. So again, if this is 30, cos would be the adjacent, root 3 over the hypotenuse, which is 2. So it'd be root 3 over 2 all squared. Remember, using our exponent laws, I didn't really use it before because 1/2 squared I thought was fairly easy. But just to remind you of the exponent laws, if I've got a fraction raised to the exponent 2, I can apply that exponent to both parts. So root 3 squared is just going to cancel out the square roots, and I'm just going to be left with 3 on the top. And 2 squared on the bottom is going to be 4. And as you can see, I end up with the same answer in either case. So I've proven that they're the same by doing them separately. The last one is just using special triangles, so not relying on our calculator to help us figure out the length of something. So we're going to still use the special triangles. 7-meter long ramp forms an angle of 60 degrees with the ground. Very steep. Exactly how high is the top of the ramp above the ground? So we got the 7-meter long ramp at a 60-degree angle. So maybe this is my 7-meter long ramp. I want to know how high that is above the ground. So if this line represents the ground, then the height of that ramp, the top of the ramp, is going to be represented by this side here, isn't it? I want to find out what I'm calling x. What I know is that this is a 60-degree angle. So, using my knowledge of trig ratios, I know that x is my opposite side, and 7 is my hypotenuse. So with opposite and hypotenuse, I'm going to set up a sine ratio. Sine 60 is equal to x over 7. And in the past, I've rearranged this and just used my calculator to tell me what 7 times sine 60 is. That would give me x, but I want the exact value in this case. I can still rearrange it, so maybe I should. If I multiply both sides by 7, I get 7 times sine 60. That's what this means. But I don't want to go to my calculator. What else can I do? Well, I can go to my special triangles again. I left them a little bit high up there, so maybe I'll just rewrite that 60-30 triangle once more so that we've got it handy. 1, 2, root 3. Again, this is something you want to memorize because you're going to, if you can just sketch it quickly like I just did, it's most convenient. So sine 60 means from this angle, the opposite side's root 3, the hypotenuse is 2, so I can replace sine 60 with root 3 over 2 because that's what sine 60 is. And then I can, just simplify this a bit. I guess I'd write it as 7 root 3, meaning 7 times root 3 over 2. That would be the exact value. It's not common for us to talk about the height of a ramp being 7 root 3 over 2 units high, or meters high, but it is exact, as I can prove by typing into the calculator. 7 times square root of 3 divided by 2. Sorry, I got it in the wrong place, though. Divided by 2. There we go. 6.1 meters. So is there... As you can see, let me go back to this for a second. Again, I've got this long decimal, which is not exact. That's the whole point of talking about exact values. This is not exact. If I wanted to give I could talk about it being 6.1 or 6.06 meters, but that's not exact. Whereas this value here is exact. So if a question asks for something that's exact, I do need to use those special triangles.